Testing on YouTube. 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 All right, we're joining early today. Leandro, oh, how's it going? And Skulitom Rivski. Dude, Sulitom Rivski, you not only do you have a llama heart, but you also have a llama profile pic. Dude, this guy's all in on the llama. All right. Just got one left. Just got to wait for that X stream to go live, and then we can go ahead and get started. This is a long paper, so I figured the sooner we start, the better. Let's turn on these lights a little bit more. Okay, Google, turn on studio light to 80%. See if that helps. A little bit better, right? All right. This one's good, guys. It's a very good paper. It's 90 pages. They don't hold anything back. Pretty much explain absolutely everything. And it actually performs quite well. This is the chart in the thumbnail, which just goes to show how good it's doing. It's a comparison with GPT-4. Wait up, I'm trying to zoom in to read your comment. Sagar Palai. Will Llama 3.1 be better than GPT 4.0 after fine-tuning? You don't even need to fine-tune it, man. It's already better. It's pretty much better at a lot of these benchmarks. The benchmarks are kind of saturated. They're a little bit cheesed, but it's pretty much on par with GPT-4. And they do fine-tune specific versions of it, so it seems like they fine-tuned a code version. They fine-tuned a multi-language version. But honestly, unless you're doing something extremely niche, I don't think you need to fine-tune this. Probably just run it zero shot for your use case. Unless you're doing something really weird. Cheb Khalid, who posts stream or Olympics? I'm here. I appreciate it. Is it the Olympics right now? Is it like the Paris Olympics, right? Let's see. Paris Olympics. It starts in 2 hours. But they probably don't start with something fun, right? It's just the ceremony, so it's just a bunch of people. Yeah, it's just going to be a bunch of ceremonies. They're going to have some guy in like a wheelchair, like light the flame, you know, and then they're going to have a bunch of kids come out and do some kind of cute dance and clap, and then they're going to, I don't know. You know, is that really necessarily fun to watch? I don't know. We got important stuff to do, like reading Llama 3.1, which I think is a very strong paradigm shift in AI. Okay, I think we're live here on X. Yeah, we're live here on X. We're just going to go ahead and get started. Let me spit out this gum. If any of you are curious, the gum that I chew before these streams is a piece of a gum called NeuroGum, which is like caffeinated, has some B vitamins. I think it has L-theanine in there as well. And then I combine it with a nicotine gum. Not a super high dose, low dose nicotine gum. But those two pieces of gum together, you get caffeine, nicotine, L-theanine, B vitamins, like It's a very powerful combo. So I use it for streams because obviously I want to be sharp. You know, I want to be quick and witty so I can reply to you guys. But I would recommend it for tests if you guys are students, or maybe if you're athletes. You know, you could use it right before a sporting event. But part of being a modern human is knowing how to use supplements and substances to your advantage. All right, let's go ahead and get started. Let's blow the official spiral didgeridoo. All right, welcome to another Hoopo stream. This one is just Llama 3.1. It needs no introduction. We're going to be going through the 90-page Llama paper. So 92 pages, Meta releasing the latest version of their Llama 3. They released earlier versions, I think just a month ago, and then they had one that was kind of lagging around, the 405 billion parameter one, which is the Frontier, kind of the biggest version that they trained, but they finally released the paper, and it's a good one. They've absolutely jam-packed with every single piece of information you can think of. So pretty great. It's like basically a 90-page summary of the current state of the art of language models. So let's read it together. Question from Sagar. What is your thought on OpenAI's GPT search engine? Is Google's search engine finally ended? I don't really think so. I think that I don't have access to it, so I think obviously in a very OpenAI way they only released it to a set amount of people, but I think that GPT search is the type of idea that someone like Sam Altman, who's really only focused about like very high level kind of, it's not a good idea, you know, because to me it's like a very uncreative idea. You're basically saying, hey, if we can challenge search, we can make our stock price go up. And that's really what he's thinking about. He's thinking about making the stock price go up and what actions can I take to make the stock price go up. And announcing a search product that would compete with Google is a way of making your stock price go up. But in reality, I don't think the search is going to be the same. I think if AI continues to grow, we kind of redefine the entire category, right? And the winner of the AI market, it's probably not going to be a search product. It's going to be some other kind of weird product that we don't actually even know about yet. It's going to be something new, right? So I think that if you're a real frontier AI company, you should be spending your time thinking about what that next product really looks like and trying creative ideas rather than just trying to re-implement the previous generation product, which is the search. But that's just my opinion. Search equals brand deals. Yeah, that's the other thing. It's that it's what is search, right? At the end of the day, search is a business model. It's a business model that's based around the idea that you sell preferential placement to advertisers, right? So whenever Sam Altman says, hey, we're introducing Search GPT, like, what does that mean? It means that whenever you type things into GPT, rather than just getting the output of the language model, now there's going to be a section or a certain percentage of the tokens that are given to you that are just paid for by advertisers, right? So he's created this marketplace where advertisers are going to be able to bid on the words and tokens that they want their words and tokens associated with. So he's just letting all the ad money come in, but that just makes for a lower quality product, you know? And I like I said, I think it would have been smarter for him to probably focus on what the next generation product looks like, which I think is more like an assistant, you know, something that runs on your cell phone. I thought the partnership with Apple and kind of having some kind of locally run assistant, like that seemed like a better direction to me than just trying to compete with Google to just sell ads, because I don't know, just lack of creativity there. How's it going, Khalil? I use ChatGPT to search for papers in my interest, but it doesn't work good. Huge potential for taking the search market. Yeah, I think it's probably just going to look like Perplexity, to be honest. Maybe they even buy Perplexity. I don't know. The the whole ecosystem might change a lot too, because here in the U.S. we have elections coming up soon, right? And we have one of the parties is the Trump, right? The dude with the orange hair, who's kind of weird, but people are predicting that this guy's going to win, and this guy is kind of buddy buddy with a lot of the tech sphere, and I think it might be the case that if this guy gets elected, they stop aggressively regulating M&A, the mergers and acquisitions, and if they stop aggressively regulating M&A, you might actually see a lot of mergers and acquisitions, especially now that the AI bubble has kind of like popped a little bit, you know, and these companies like Perplexity that raise these huge rounds, they're not going to be able to raise a 10x bigger round, so they're probably looking for an exit door. And I think that if you change the political environment here and the regulatory environment here in the US, you might actually see a string of acquisitions over the next couple years. So I don't know. How's it going, Jai? I tried the Llama 3.18b. It is very good. Yeah, it does seem pretty good, and they trained in a very interesting way. So let's actually get into the meat of this presentation. We got 90 pages to get through, so we're going to be here a while. Strap in. All right, the Llama 3 herd of models. This paper isn't even on archive, you know? So, like, they just don't even give a shit anymore. You know, the scientific publishing is kind of starting to get refactored. People are realizing that having these journals doesn't make any sense. And then for a long time, people had archive, or at least you could post your paper on archive before it was accepted into these journals, which made things a little bit better. But now they just don't even go on archive, dude. They just post it on their website, which is, I actually think it's a good idea. You know, you don't need to go through these middlemen, these so-called journals that are providing distribution, because the internet basically gives you infinite distribution. You don't need to rely on those people. So just put your paper right on the internet as soon as it's done, and there you go. People will read it. So the Llama 3 herd of models, right? Obviously there, the word herd referring to the fact that there's a bunch of llamas. I think herd of llamas, right? Is it an ungulate? I don't know. Ungulate, right? What's the word to describe ungulate? Yeah, ungulates. Are llamas ungulates? They are. They're specifically tylopodas. Okay. Let's get this abstract. This paper's so big that it crashes the paper reading. It's like a 90-page PDF. It's probably absolutely destroying my RAM. But we have a herd of language models that natively support multilinguality, coding, reasoning, and tool usage. Obviously missing there is multimodality. So it seems like they were trying to do this, though, because if you see here, they present the results of experiments in which we integrate image, video, and speech capabilities. So it seems like they probably tried to add multimodality, right? Adding the modalities of image and the modality of audio, but they didn't quite get it to work, so they just decided to cut their losses, just publish the paper. It's just really just an LLM, and that's it. So 405 billion parameters, which is a lot of parameters. That kind of puts it outside of the size that you can even use locally. So it's a little bit weird because it's an open source model, but like most people can't run this. Even if they quantize this on their home GPUs, right? You kind of need to run this on server nodes. So I see it more like a foundation model that's intended to be distilled into some specific use case or used by a small business. And yeah, maybe a little bit different than the 8B, 13B, although they do also release small versions as well. Context window of up to 128K tokens. Context window starting to get to that point where you don't need anymore, right? 120. It's kind of like how memory was in the early days of computer, where initially it was a very limiting factor, just how much memory was available. But then once you started to get megabytes, gigabytes, then at some point the memory stopped being an issue. And I feel like we're kind of starting to get to that point with a context window as well. Like 99% of tasks that you want to use these models for, I feel like 128,000 tokens is probably more than enough, but probably that's going to keep going on until probably like a couple million, right? I feel like at some point the context window stops being a thing. Yeah, so Sagar is saying you need about 200 gigabytes of RAM to run this locally, which is more VRAM than you have in any consumer GPU, or even if you max out all the PCI slots or PCIe slots on like a consumer motherboard, I don't think you can even get to 200 gigabytes of RAM. So you definitely need a server rack for this. Okay. So we seek to optimize 3 levers in our development process. They're going to be looking at data. We're going to be seeing more careful pre-processing and data curation pipelines. This is a story that we are seeing time and time again where data is the most important thing. In fact, they don't even really change the architecture much. So they do mention here that they use a standard dense transformer model architecture, basically almost identical to the Llama 2, just a couple little different tricks. Relatively simple post-training procedures. They're still using SFT. They're still using DPO. So like there's not necessarily a huge amount of algorithmic differences between Llama 3 and Llama 2. Really, a lot of it is just kind of in the engineering best practices, right? So now there's a lot more data curation. They're doing synthetic data generation is a big part of the story here as well. It's all the little pieces around that they improved, right? Kind of engineering versus research and science, I would almost qualify that as. Over 15 trillion tokens of training data, and they trained it for 3.8 to 10 to 25th flops. So this is basically kind of how much training happened, how many floating point operations occurred, and then this is how many actual individual tokens of training data there was. So a 10x the amount of training data compared to Llama 2, and then a 50x more training kind of duration or compute than the Llama 2. So they kind of 10x'd the data, and they also 10x'd the total amount of training time. Okay, the scaling laws. Our model outperforms smaller models trained using the same procedure. People are talking about these scaling laws a lot, but one thing that I kind of got after this paper is that these aren't laws as much as they are hypotheses, right? So I would say that we need to think about these more like scaling hypotheses rather than scaling laws, because a law is a very strong word, right? That means that's something that is guaranteed, that almost has like some kind of basis in physical reality. But like these scaling laws are kind of more like Moore's law, right? Where Moore's law isn't really a law because it's changing, it's slowing down. And the same way, these scaling laws aren't really laws because, as they say here, they can be noisy and unreliable. So we're not 100% sure, right? And it could be the case that what we think is a straight line like this actually becomes kind of a exponential, or maybe it becomes a sigmoid and it flattens out. So don't put too much trust in these scaling laws, because I don't think they're 100% going to continue their trend. 8B, 70B, and 405B. So 8B model is going to be the one that you actually run on your computer locally. And I think these 8B and 70B models, they actually distill them in a way from the 405B model. So not like direct distillations where they're kind of just doing distillation the way that you would do distillation right now, where you like have the big model, you put an input into the big model, see what that big model outputs, and then just kind of almost as a supervised train the small model to do that as well, right? To mimic the big model. I think in this case, what they were doing is they're actually using the bigger model to synthetically generate examples to then train on the small model. So the training curriculum and kind of all the different parts of training are definitely starting to get a little bit more complicated, but you know, the performance is there. So here they have the table 2, the big benchmark table. So this is where they're going to be comparing to all the different open source model, or all the different competitor models. So you have some open source models here like Mixtral, but you also have the kind of frontier closed source models here like GPT-4o out of OpenAI, and then Claude 3.5 Sonnet out of Anthropic. And you can really see that the Llama 3 405B is kind of really basically there. You know, it actually kind of beats on some specific benchmarks, but on all the other benchmarks, it's kind of basically within 1 percentage point every time. So look at this. It tool use, BFCL 10% points greater than GPT-4o at tool use. GPT-4o is definitely smaller than 405B, but still impressive that we now have an open source model that is effectively as good as the closed source models. And I think that changes the AI market a lot, because it means that a lot of these closed source companies that were kind of hoping that their closed source and secret sauce would allow them to deliver a higher quality model than everybody else, that's not going to be the case. So what's the point of being secretive and closed source if your model is actually worse than the open source versions of the model? So open source hitting a big win here with this Llama 3 release. General overview. So let's see. Language model pre-training. Converting a large multilingual text corpus into discrete tokens. This is the process of tokenization. And then ultimately they're just training this, at least in the pre-training stage, on next token prediction, right? So just which of the 128,000 tokens in the vocabulary is this next token given this context that I've currently accumulated. So same exact training objective as all previous language models. They start with a small context window and then gradually increase the context window. I think they do 6 stages of context window. So they start with an 8K tokens and they end up to 128K tokens at the end. The instruction tuning, here they're calling it post-training. There's a couple different words that have come up for this. This is probably the area where we're seeing the most kind of movement, but they're still just using DPO and SFT. Multimodal encoder pre-training. Separate encoders for image and speech. So this is different than what we saw for Chameleon. Chameleon was another paper that came out of Meta where they actually, I don't think they had encoders for images and speech. They tried to basically project all the modalities at a very low level in the model architecture, versus in a lot of open source vision language models and open source text-to-speech models, like, or I kind of know VLMs a little bit better than the speech ones, but in VLMs, kind of something like a Llama or even the Apple VLM, you're feeding your image into this image encoder, which is pre-trained on some other task, something like a clip or something like a dyno or something like that. That'll produce an embedding which represents that image, right? So some encoded representation of that image. And then you have this little, what people call a connector. Here in this paper, they call it an adapter. And that adapter converts that encoded representation of the image into a sequence of tokens that you then feed into a language model, in this case, Llama. So they're kind of using the old school style of multimodal, adding multimodal abilities to a language model, but I don't know why they didn't necessarily add it by default. It seems like it probably just didn't work as well. So they have actually later on in the paper, they have some sections talking about the multimodal experiments, as they call them. Okay, figure 1, illustration of the overall architecture and training of Llama 3. Llama 3 is a transformer language model trained to predict the next token of the textual sequence. Okay, so you have input text tokens, get some token embeddings, right? So you tokenize, and then each of those tokens has some vector of numbers, which represents the kind of information in that token, the semantic meaning of that token. That's the embedding. That embedding goes through a bunch of blocks of transformers. Each block of a transformer, there's really 2 kind of key parts here. There's what's called the self-attention. This is the quadratic complexity part where you're taking every part of your sequence, giving it the opportunity to kind of look at every other part of the sequence. You get these attention operations, right, where you're multiplying these queries and the keys. You use that to filter how much of the values are going through. And then the second part of the transformer block is what's known as the multi-layer perceptron, sometimes also called the feed-forward network, FFN, but it's basically just a classic multi-layer neural network. And that's the 2 main parts, and then you just basically stack a bunch of those blocks. I think they stack specifically 126 layers in the 405B model. And then at the very end, you have your basically like a classification head, right? It's just picking which of the 128,000 tokens in the vocabulary is the best one. And then autoregressive decoding here basically means that once you pick the next token, you add it to your context, and then you run the whole thing again, and then picks the next token after that. So you can only predict one token at a time, unless you're doing something like speculative decoding, but they don't mention that here. What else? Pre-training data. What is autoregressive decoding? I just mentioned that, but yeah, it's the fact that you're regressing on your own output. So it's like you output a token, and only after you output that token can you get the context to then output the next token. So it basically means you can only you decode one token at a time. That's basically what it means. Is not Clip model as OpenAI? Yeah, OpenAI has a Clip model. Clip is not a model architecture as much as it is a training method, right? It's a contrastive learning method where you use images that have associated text in order to train encoders for images that allow you to kind of extract the semantic information in an image. But not all Clip models are from OpenAI. There's other clips that are trained by other companies, and even I'm pretty sure Meta has their own kind of clip-based models, but they also have their own image encoders that are pretty strong. Meta is the company behind Dino, which is one of the stronger image encoders as well, and they're the company behind the Segment Anything model, which is pretty much the state-of-the-art segmentation model, and the encoder on that state-of-the-art segmentation model is very strong as well. Is there a reason why current models don't implement infinite context from the paper, leave no context behind? Yeah, there's a bunch of other tricks to have infinite context. Linear attention models like Mambas and LSTMs also technically have infinite context. There's other fancy ways of getting longer context, but I think you just don't really need it. I think that 99% of the use cases that you run into, you don't need infinite context, right? You're like answering like a sentence with another sentence. So I don't think that pushing this context window to a bigger size was necessarily a big driving requirement, right? Because they could have done 1 million. Like, we know that, for example, the Google Gemini models have like something like 1 million token context, but that's not really a feature that's making them better than the other competitors. So I think at some point a decision was taken here that like, hey, we don't really need to have a massive context window. 128K is totally fine. Okay. These adapters, so adapters for the vision and the speech. Pre-training data. I think this is a big part of it, right? This data cleaning. I don't breathe in through my nose when I talk, and then I just end up sounding plugged. So the pre-training data comes from a variety of data sources containing knowledge until the end of 2023. This is the only part of the paper that they don't talk too much about, and that I wish they would have talked a little bit more about, is kind of specifically the data mix and like, where are you getting this data? What is this data? Like, is it textbooks? Is it you're scraping Reddit? Is it like, what the fuck is it, right? But I think part of the reason they don't mention that is because from a regulatory perspective, we don't really know whether people are going to get sued for using publicly available data, right? Whenever they say publicly available data, that means that you as a human can go on the New York Times website and read all those articles. Does that mean that it's okay to have a scraper bot scrape all of the New York Times data and then train on it? Yes, no, it's like we don't really know yet. So I think Llama and the Meta as a company and OpenAI as a company, they're being purposefully vague about where their data comes from because they don't really know the legal ramifications of admitting that they scraped YouTube or admitting that they scraped Reddit. So that's unfortunately why everybody's kind of being secretive about where exactly the data is coming from. But what they have no problem talking about is deduplication and data cleaning, which I think is a very important part of pre-training data creation, is filtering, right? So they talk about filtering based on whether or not it's porn, right? That's what adult content is. But also they parse all of it. It's going to come in HTML, right? Because they're scraping these websites. And they're going to do several rounds of deduplication. So deduplication happens at several levels. And you can deduplicate in a lot of different ways, right? You can have heuristics, which is someone wrote some hard-coded stuff, like basically think about a bunch of if-else statements that like filter out specific things. But a lot of deduplication is also being done using language models themselves. So you might take a whole paragraph, you might embed it into some vector that represents the content of that paragraph. And then you see and compare that embedding to other embeddings of other paragraphs that you've looked at. And if it's too similar, then it basically means that the content in that paragraph is the same as the content in some other paragraph. And therefore, you can kind of deduplicate by removing that. So there's a lot of deduplication that they do here. One interesting thing that they've found here is that Markdown is harmful to the performance of a model that is primarily trained on web data. So we remove all Markdown markers. This actually changed the way that I prompt. So actually, when I used to prompt these models, I would actually, for example, like if I was prompting for code, I would say, what is the output of this code? And I would sometimes do this, right? For blank in blank, blah, 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 blah. And I would do this. And what I was doing here is this is Markdown. So I was basically, in my mind, I was like, okay, if I indicate it like this is better than if I do this, right? Than if I just literally give it the code like this. I had no reasoning for doing that. I just kind of assumed that maybe this Markdown format would be better. But ever since I read this line on this paper, I no longer do that because now I realized, okay, Markdown is harmful. So actually, you probably don't want to have the Markdown format when you're giving your language model questions, especially if they removed it from the training corpus. Heuristics, dirty word counting to filter out adult websites. So some kind of meta engineer is sitting there looking at a bunch of porn websites probably. Token distribution divergence to filter out documents containing excessive number of outlier tokens. Okay. KL divergence is a metric that allows you to determine the distance between two distributions, in this case, distributions of tokens. So if you have documents that have weird token distributions, maybe it's like someone who like typed every single emoji on a Reddit comment thread, you can kind of immediately see, okay, the distribution of tokens in this weird piece of text here is very weird. Let's not include that in the pre-training corpus. Model-based quality classifiers. So you have models that are filtering the pre-training corpus for you. Question from Josh. Did they suggest an alternative for defining hierarchical data other than Markdown? I don't know if Markdown's necessary. Like you're talking about how Markdown, you can have like the title and then the subtitle. So like Markdown is not just a way of kind of formatting. It's also a way of kind of organizing the title and the text and stuff like that. HTML has a similar kind of structure to it, right? You can kind of define hierarchical data within HTML with like tags and titles and stuff like that. So I don't know. Maybe we remove all Markdown markers. Yeah, I guess they just get rid of that hierarchy data and just it learns the hierarchy of the data implicitly. Not 100% sure. Determining the data mix. It is essential to carefully determine the proportion of different data sources in the pre-training data mix. They use a classifier to categorize the types of information to more effectively determine the data mix. They downsample specific categories. So I constantly use the example of like if you were to train a binary classifier to classify images of cats and dogs, right? You wouldn't want the mixture that you train on to be like 90% dog images and 10% cat images. You want those to be more balanced. So there's a similar kind of intuition for text data as well. You don't want 90% of your data set to be arts and entertainment. So they use a classifier, which is just a language model that classifies a blob of text into one of whatever 100 different categories, and they downsample the ones that kind of keep popping up a lot. They perform scaling law experiments to train several small models on a data mix and use that to predict the performance of a large model on that mix. I thought this was important because this is something that we see for a bunch of other hyperparameters, right? For all the different architecture hyperparameters, they usually will figure out or sweep the hyperparameter space in small models, right? Because in order to evaluate the value or evaluate which hyperparameter value is the best, right? Let's say the number of heads, right? So like, for example, here, the number of key value heads, right? You don't want to train 10 different 405 billion parameter models, one that has 2, one that has 4, one that has 8, one that has 16, right? It's like, that's just going to be way too, you can't do that much training. So you're doing all your hyperparameter sweeping at lower model sizes and then just kind of extrapolating or assuming that the correct hyperparameters for the small model are also going to be the correct hyperparameters for the big model. So we're now starting to see people do this for the data mix as well. So you're not just using these little scaling law experiments to determine hyperparameters, but now also to determine the data mixture, which I think is a good idea. Ultimately, 50% of the tokens come from general knowledge, 25% math, 17% code, and 8% multilingual. So kind of I don't know if that's low or high, but 17% code is not insignificant, especially since a lot of that is synthetically generated. Annealing with data mix that upsamples high-quality data in select domains. And actually, the more interesting thing here that I found in this paragraph is that the improvements on the 405B model are negligible, suggesting that our flagship model has a strong in-context learning and reasoning capabilities and does not require specific in-domain training samples to obtain strong performance. So, scale simplifies. What I meant here by this comment is that sometimes when things get bigger, they get more complicated, right? Training on one GPU at home is way more simple than training on 1,000 GPUs in the cloud. But here we're actually kind of seeing an opposite trend where when you're training a small model, you have to kind of use this annealing and use a special type of post-training in order to get the Llama 3 8B model to perform well on GSMK, 8K, and math. But you don't need those little tricks to improve the performance of the 405B model. So this is actually the real scaling law, right? And the real scaling law is that as you keep making these models bigger and train them for longer on bigger data sets, a lot of the little tricks and hacks that you have to use for the small model training, you actually don't need to use them for the big model. So the big models are capable of generalizing and they're more robust to not having all these little tricks. And I think that is kind of what's going to allow us to get to ASI, is that as we continue to train bigger and bigger models on more and more data, we're not going to need to have all these little tricks, right? So the total amount of special one weird tricks actually reduces as you scale these things up and up and up, which is going to make ASI possible, right? If that wasn't the case and everything just got more and more complicated as you got bigger and bigger and bigger, then it would take us a while to get to super intelligence, but I think it's actually going to get easier as it gets bigger. Okay. In terms of the model architecture, like I said, they really didn't do much here. It's still the same dense transformer architecture from this Attention is All You Need paper, this Vaswani 2017. Dude, this guy has probably an insane amount of citations at this point. Does not deviate significantly. Our performance gains are primarily driven by improvements in data quality and diversity. Yeah, so it's all about training longer on a more varied and larger data set. And the size of the data set effectively is the diversity as well, right? So it's not like you can take a data set and then just 10x it and you somehow, like, it's somehow better. No, it's like you need... The dataset size is really just a proxy for the dataset variance, and that's really what you want is a full coverage of all the data space. So dataset scale is really just a way to get to a more varied dataset, or dataset diversity as they call it here. Attention mask that prevents self-attention between different documents within the same sequence. So this is a little trick where whenever you're doing this long context pre-training, right? So they're increasing the context length over the course of the training. They're starting with the 8K and then going all the way to the 128K. You're going to end up with certain situations where you're predicting the next token, and the first part of the context is like some unrelated document to the second part of the context, right? So they use this attention mask, which basically means that if you have two different documents that are going to just happen to be connected to each other because you're training this long context model that's doing next token prediction, you mask out, or basically kind of think of it like zeroing out the attention between one document and the other document so that you don't get kind of weirdness there. So just a little trick that you have to deal with. But going back to what we were saying here, maybe this is something that disappears. Maybe as you get a bigger and bigger and bigger model, you don't need to be doing this attention masking to prevent self-attention between different documents. So the tokenizer. So the tokenizer is what takes your raw text and then turns it into these little tokens, right? And these little tokens, there's less of them than there are individual letters. So you get this compression. So rather than having 100 letters or 100 letters in a sentence, you now reduce that by this factor of 3.94. So every token is roughly around 4 characters. And the vocabulary size, this is mostly comes from TikTokin, which is, I think, probably the most popular tokenizer. This is, I think, the same one that Karpathy used. It's probably the same one that OpenAI uses, probably the same one that everybody uses, to be honest. With just some slight modifications, they added an additional 28K tokens, but 100,000 words, is, you can think of it that way, is there's 100,000 possible words. When you're autoregressively predicting the next word or the next token, you're basically picking one out of the 128,000. Here they have the hyperparameters of Llama 3. So you can see the different hyperparameter values for the different sizes. You can see the 8B model only has 32 layers versus the 405B model has 126 layers. Also increasing on the model dimension, the FFN dimension. This is the little multi-layer perceptron, so how wide that is. Number of attention heads also increases. The peak learning rate decreases. So this is interesting here, right? You're training small models. You can train them with a bigger learning rates. Big models, they're a little bit more fragile, so you have to train them with a small learning rate. So you can see that difference in learning rate there. The position embeddings, this is the extra piece of information that you add in addition to the tokens that lets the model know specifically within the sequence, where within the sequence this token is. And there's a lot of progress that has gone into this. I think we actually even reviewed the rope paper on this channel, so we should have a video about that if you're interested. So nothing new there, just rope embedding. So it seems like we've kind of plateaued on these position embeddings, and I actually think that we are not going to need the position embeddings eventually. I don't like these position embeddings because they're basically these like hard-coded like sines and cosines that you kind of like have to define with all these random arbitrary hyperparameters here. So they're like, oh, we use this like theta of 500,000. It's like, this is just some fucking weird number that some human came up with, right? It's like, I think at some point we're going to learn these position embeddings, or they're just going to be more kind of baked in. So I don't know. I think these eventually go away, but for now they're still a key part. Scaling laws. Scaling laws. I already touched on this, but the scaling laws, I think they're more just scaling hypotheses, right? It's like, I think there's too many other weird trends that I think that if you 10x again, if you 10x the data again, and you 10x the model size again, I think some of these scaling laws might actually disappear and you might see different behavior. So with these scaling laws, what are you trying to do? You're ultimately trying to predict the downstream task performance given a specific number of training flops. I think they have a chart here. Yeah, for example, here, scaling law forecast for the ARC challenge. The ARC challenge is Francois Chalet's kind of abstract reasoning challenge. It's like a benchmark. It's like the benchmark for all benchmarks that he like created. It's like this weird, like, you're like trying to predict little like grid things. So like it's like a little shapes and you're trying to predict the shape. It's like all about like symmetry and rotation and kind of things that humans are very good at because we have a very good kind of visual encoder. So the ARC challenge is kind of that same, trying to get to that general human intelligence, right? Designed by Chalet, who's the guy who made Keras, so kind of a famous guy. But what they're doing here is they are training small models and then saying, okay, based on the amount of training or flops that we put into this model, what can we expect the performance to be on this ARC challenge? And you can see that they all actually follow a nice little trend, right? So they trained a bunch of little small models. That's what these little, what is that, red squares are. So they trained a bunch of small models for slightly longer amounts of time. And you can see how they follow this thing. And then they're like, okay, according to this, we should be able to predict what the big model is going to perform, right? Because the big model, they can only run one of those training runs because it's so huge, right? Versus these small little models, they can try a big hyperparameter sweep. They can train them with a bunch of different things, or a bunch of different hyperparameters. So this is actually quite accurate in terms of the predictive power of your scaling hypothesis, right? Because you can see that they predicted that it would be about here, and then boom, it's right there. But actually, you can see it's actually a little bit better. And same thing here, it's just a little bit better. So kind of interesting that they predict them well, but I still feel like technology is just a bunch of S-curves. We're kind of hitting the top of the S-curve here for language models, but I think there will be other breakthroughs where these scaling laws no longer apply, right? So I think, for example, once you start incorporating some of these linear attention modules inside these models, you might get a completely different type of scaling law, right? So one thing that I see here is that Llama 3 is just a bunch of transformer blocks with full self-attention, right? What we're seeing become more and more popular nowadays are these more complicated architectures that have basically self-attention blocks, but then they'll also weave in Mamba blocks or LSTM blocks. And I think that type of model might kind of have a different scaling law than what we're seeing here. So yeah, like I said, I think the main story I want you guys to get out of that, or the main opinion that I have, is that I don't think these scaling laws are necessarily the laws that they say they are. I think they're mostly just guidelines. Cosine learning rate schedule. This is also pretty standard. Nothing new there. Fixed batch size for each compute scale. These batch sizes are kind of magic a little bit too. You know, they're kind of picking them based on the actual data center as well. So they're like, okay, based on the size of the data, based on the context, based on how much memory is in each of these GPUs, based on how much like information are we sending back. There's like so many real world numbers that end up influencing what batch size you pick. And then even within that, the batch size isn't actually exactly what is happening. It's also like you have this concept of a mini batch where you have the actual batch size at the theory level, but then you have the mini batch, which is actually like what you're actually running through what you're pushing through each GPU. So these numbers seem kind of big, but they're kind of arbitrary as well. Everything is arbitrary, I guess, once you get to this point. Compute budget, optimal number of training tokens. So this is how do you choose the size, or how do you choose how long to train on when you know your data set size? So you're like, okay, I know that I have 15 trillion tokens of data. How long should I train this model that has this specific size? And this is kind of the scaling law, right? Isoflops is flops, but iso basically means the same. So why do we use isoflops? Because there's different hardware configuration. It's like not every flop is the same. So now we've kind of developed this kind of hardware agnostic, kind of data type agnostic flop, which is called the isoflop. We establish a sigmoidal relationship between the log likelihood and the accuracy. That's this one here that I showed you guys. See this sigmoid? So it's an S-curve. It flattens out, which is kind of what you're seeing, right? Because if you actually look at the accuracy of these benchmarks, we are kind of flattening it out. So what this tells me is that OpenAI and Anthropic, there's no secret sauce there, right? They're kind of getting the same scores as Llama 3. So I don't think there's any secret sauce at OpenAI or Anthropic. I think it's like everyone's largely basically building the same technology because all the technology sits on this S-curve and it's all kind of flattening out at the same time. So we're still waiting for someone to come up with the next S-curve, which I think is going to be some kind of, I think it's going to be something related to the linear attention and putting in Mambas and this kind of hybrid architecture that I'm talking about, but it could be something completely out of left field that we have no idea what it is, right? So we're still waiting for the next S-curve to drop. All right, this is the coolest part of this paper, which is where they talk about the research supercluster. So this is basically the computer that they trained this on, and it's not just one computer, right? It's this massive like building just filled with all these fucking computers, all connected in all these fancy ways, and they go straight into it, right? They don't hold back. They tell you everything about it. So you got 16,000 H100 GPUs, which is absolutely fucking insane. And that gives you a scale of the one that Elon has. I think Elon's supercluster that he made is 100,000 H100 GPUs. So it's another order magnitude on top of that. So kind of excited to see what Grok is going to look like. And hopefully they release the paper, right? Hopefully Elon joins Team Open Source. And as soon as the Grok, whatever, I think it's V2 or V3 that they're on right now, gets trained on those 100,000 H100s, and hopefully they publish a paper and release it. But we'll see whether or not they do that. Each H100 runs at 700 watts, which actually seemed kind of low to me. I feel like H100s are so big that like I automatically assumed these things were consuming more than 700 watts. Like my 3090 consumes like 400, 500. So like how does an H100 consuming 700 only? That seemed kind of low. But 80 gigabytes of high bandwidth memory. So that lets you know basically how much, it's kind of like how much VRAM there is. But once you get to these more complicated GPUs, the distinction between just like RAM on your computer and then VRAM on your GPU, it's like more complicated than that. There's different levels of VRAM on your GPU, different caches as they're called, right? You have caches that are closer to the cores, caches that are further away. And then once you start talking about these server racks, it gets even more complicated, right? Because you have the RAM that's close to the GPU, the RAM that's kind of outside of it. As they call it here, you have a distributed file system, over 240 petabytes of storage. And out of the 7,500 servers equipped with solid-state disks, they can basically peak throughput 7 terabytes per second. And one challenge that they talk about here is supporting the highly bursty checkpoint write. So what do they mean by that? Is that occasionally, as you're training the model, right? And when you're training the model, you're largely just taking a chunk of data, this mini batch, you're pushing it through the actual model, right? So actually doing the self-attentions and the MLP, like actually calculating the matrix multiplies for that. And then you're going to get some output, and then you're going to take your loss function and use that to back propagate through your model. And then once you back propagate through your model, you're going to get basically this gradient, which is effectively like a little change in all the weights, right? So you're basically saying, okay, this little neuron right here has some weight right here. I want you to change that to this. This little neuron here, it has some weight right here. I want you to change that to that, right? That's effectively what a gradient is. It's basically a little delta for your weights. And once you change your weights, you're going to maybe want to do what's called a checkpoint. A checkpoint is when you say, okay, I have all my weights in this particular set. I have all my gradients. I have maybe some optimizer parameters as well. I'm going to want to save all of those, because if something happens, I want to be able to reload this current state that I'm at, and that's called the checkpoint. But whenever you're writing that checkpoint, what do they mean by highly bursty is that now all of a sudden you have all these GPUs that all want to store at the same time. So you basically just suddenly have 16,000 GPUs that are like, hey, I want to store my little state into this 240 petabytes of storage. So unfortunately, because of the way training works, all of these little GPUs, they're all kind of like working. It's not synchronous because there's some level of asynchronous kind of compute happening, but they all kind of want to consume and then write more often than not kind of in tandem. So supporting that kind of like bursty, like nothing's happening. Now suddenly everybody wants to write their checkpoint. Now nothing's happening. Now suddenly everybody wants to write their checkpoint, right? So that's a really weird compute. What am I trying to say here? It's a really weird usage plot. I don't know what there's some specific word for that, but training is weird. Training workloads, that's what it is. It's a weird workload. It's a weird training. Workloads are weird. Each server is equipped with 8 GPUs and 2 CPUs. So that's when I talk about a server rack, that's what I'm talking about, right? So this is the server itself is this big, I don't know, depends on what you want to call the rack or the box or whatever you want to call it. But basically you have this tower, and inside that tower, there's these little slide-in kind of boxes like this. And then inside each of those slide-in boxes, let's see if we can actually get server box picture of one. I want a picture of one without the cover. I don't think I'm going to get one. But anyways, within each of those, you have these, right? And then within each of these, you have this. So you have basically 8 GPUs, 8 H100s, all connected via NVLink, and they have 2 CPUs, and these CPUs, basically what they're doing is they're just shuffling data in and out of these GPUs. So that's the main workflow there, is that you have some computers, which are literally just kind of storage computers, and they're taking some data, which is stored in SSDs. They're shepherding that via this fancy NVLink stuff. I think there's actually different. The networking that's in between the GPUs is different than the networking that's in between the different racks, and that's different than the networking that's in between the different rooms in this data center as well, right? So the networking gets very complicated very quickly. I'm getting lost in the weeds here. What were we talking about? Network. So they use RDMA over converged Ethernet, 400 gigabyte per second interconnects between the GPUs. And why is that important, right? Well, because each of these GPUs has 80 gigabytes of basically VRAM. So if you change the data set or you update the model, right, you're basically taking everything that's in that VRAM, putting in something new. So 400 gigabytes per second means that you can basically clear out 4 of those GPU memories in 1 second. Each rack hosts 16 GPUs. 192 such racks are connected with cluster switches to form a pod of 3,072 GPUs, and then you have 8 such pods within the same data center building. So in the data centers, you have these pods. Inside those pods, you have the racks, and inside each of those racks, you have the actual nodes, and inside each of those nodes, you have 2 CPUs and you have 8 GPUs. So that's kind of the hierarchy of compute hardware there. This is the section that I feel like we should get George Hotz to read, because I feel like this is exactly the type of shit that he needs to be thinking about with the tiny box, right? Because the tiny box is basically a tiny version of this, but like all the same problems apply. And one interesting one, I'm going to come back to this parallelism, but like one interesting thing that they talk about here is this here. I'm going to come back up to this. Yeah. Tens of thousands of GPUs may increase or decrease power consumption at the same time, resulting in instant fluctuations of power consumption across the data center on the order of tens of megawatts, stretching the limits of a power grid. Right? They found that there is an impact of environmental factors. So a diurnal 1 to 2% throughput variation based on the time of day. This fluctuation is the result of higher midday temperatures impacting GPU dynamic voltage and frequency scaling. So as the day goes, right, and during the day the sun is beating down on this data center, which means that the GPUs are just running a little bit hotter during the day than they're running during the night. And when you have tens of thousands of GPUs all kind of just blasting at the same time, and they're not just blasting at the same time, but they tend to like, they're saving checkpoints kind of around the same time, right? They're all kind of like requesting more data at the same time. They're all pushing gradients kind of, so like, the workload is all kind of like more in sync than you would want it to be, to the point that you get these weird increases and decreases in power consumption around the same time, which results in fluctuations of power consumptions across the whole data center. So one thing that I kind of got out of this paper section here is that energy is becoming a bottleneck, right? And this is a narrative that we've seen time and time again, even to the point of like Sam Altman talking about using kind of fusion power, nuclear power plants, where you can have a more controlled, you can have more control over the power consumption and the specific, like, I don't even know if it's voltage is what they're thinking about when you think about the power consumption of a data center, but you want that to be standard. And I wonder if getting to the next S-curve of technology for LLM training is going to require not just designing the GPUs and designing the racks and the pods, but also designing the power plant that goes with the GPU, right? So I feel like that's something that's coming down the pipe. I think it's probably 5 years away, but I think 5 years from now or 10 years from now, we're going to have these data centers aren't just going to be, hey, here's the GPU and here's the network interconnect between these GPUs. It's also going to be like, hey, here's a specialized like fusion power reactor that like can deal with these weird power fluctuations that you get when you have tens of thousands of GPUs kind of all working on the same problem at the same time so that they're kind of bursty. Nuclear AI. Yeah. I wonder how quickly an SSD runs out of its resources while a huge model is training. Yeah, I think they should. I don't know what you mean by resource there, but right, like the SSD, way better than the HDD, right? Because it's faster read and write. But I don't know how much, because there's different SSDs, right? Like some of the SSDs are just holding the data set, right, which has been sharded, and those SSDs you're pretty much only reading from them, right? But then there's other SSDs that are holding things like the model checkpoints, and those are kind of reading and writing. So even within the nodes that have access to the SSDs, like there's probably different workloads there. Okay. Parallelism. So there's 4 types of parallelism, okay? There's what's called tensor parallelism, pipeline parallelism, context parallelism, and data parallelism. We've gone over these before, and you can see here's a bunch of papers where each of these concepts were introduced, but at this point, they're using all of the types of parallelism. So I thought this was a nice little summary of all the types of parallelism. We got tensor parallelism splits individual weight tensors into multiple chunks on different devices. Pipeline parallelism partitions the model vertically into stages layer by layer so that different devices process in parallel different stages of the full model pipeline. So tensor parallelism will basically say, okay, half of the self-attention here is being done by one GPU, the other half of the self-attention is being done by a different GPU. Pipeline parallelism says, okay, this block here is being done by one GPU, and then this block here is being done by a different GPU, right? So you're kind of separating out by the layer, separating out by the tensor itself. Then you also have data parallelism, which is, okay, this part of the batch is going to be done by this GPU, this part of the batch is going to be done by that GPU. And then context parallelism, which is saying, okay, this part of the input context is being calculated by this GPU, and this part of the input context is being calculated by that GPU. But it's actually more complicated than that because all 4 types of parallelism are happening at the same time, right? So every single GPU is really divided into parallelism groups. So all GPUs are really just seeing one slice, one 4-dimensional slice across all of these different parallelism dimensions. So it's really kind of like a compute mesh is kind of what people use to describe these systems. So a GPU's position in this 4-dimensional parallelism space is represented by this vector D1, D2, D3, D4, where Di is the index on the ith parallel dimension. So if you had your input context was being split into 2 pieces, right, then half of the GPUs would have index 0, and then half of the GPUs would have index 1, right? But it's being split up in many more pieces than that because you have many more GPUs than that. But you can see the device mesh there, I suppose. GPU utilization. Still only getting about 40% utilization. So this kind of just lets you know what the weak link in the chain here. It's not the tensor core. So it's not even the actual chip in the GPU that's performing the matrix multiplies that is the weakest link in the chain. Really, those tensor cores could be operating twice as much, right? That's what a 40% utilization is telling you, is that 50% of the time they're just kind of sitting there doing nothing. And why are they sitting there doing nothing? Is because they're waiting. They're waiting for all the data to get given to them by the CPU and the SSDs, like all of the communication, all of the overhead of sending this data back and forth between all these different GPUs. That means that 50% of the time your GPU cores are just sitting there waiting for the next batch, or waiting for the checkpoint to finish, or waiting for the other GPU in the layer in the pipeline parallelism to finish the output of that layer so that you can get it to this one, right? So gets quite complicated quite quickly. And here's a diagram which you can see that the way that they try to solve some of these things, right, here specifically in pipeline parallelism, right, pipeline parallelism is whenever you have some layers, maybe the beginning layers being done on some GPUs, and then the later layers being done on different GPUs. The problem with that is that now these GPUs doing the layers at the end need to wait for the GPUs here to finish. So what people do is they basically stagger these things, right? So you can see here how stage 0 to 3, stage 4 to 7, you can see how they're staggered. So like the GPUs aren't all calculating the same batch at the same time, because that would mean that a lot of GPUs would be waiting on the output from some other GPUs. So everything is kind of staggered in this weird way. And that solves some problem, but like if you just have one GPU, like if the GPU right here that is calculating this 3 suddenly stalls and breaks, then the GPU here that is waiting for the output of that 3 is going to have to wait. And then the GPU that's waiting for the output of that GPU is going to have to wait. And then the output that's waiting for the output of the waiting for the output. So it's like very quickly, these staggered systems, even though they solve some of that utilization problem, they, no matter what, the training job is still very interrelated. So like even if you just have some, like a tiny amount of failures, you can have a big problem with that. And they do talk about the failures here. Let's finish this though. The order of parallelism dimensions, TP, CP, PP, and DP, is optimized for network communication. The innermost parallelism requires the highest network bandwidth and lowest latency, and hence is usually constrained to within the same server. Okay, so within the same server node, right? So you have this server node here, which they say has 8 GPUs. Where is it? Somewhere here? Right here. Right, so each node has 8 GPUs and 2 CPUs. So that node has the fastest communication between it, right? It's going to be a lot faster to communicate between 2 GPUs that are sitting on the same node rather than one GPU that's on one pod and another GPU that's on a completely different pod, right? So like the same way that you have these memory caches within the GPU itself, you can think of the whole data center as basically a hierarchy of caches as well, right? Where certain SSMs, SSDs are going to be closer to other GPUs, and you want to make sure that that parallelism accounts for the kind of hierarchy of caches and the communication speed between them. So they did a bunch of thinking in that, and ultimately they came up with this order. First, you have tensor parallelism. So within the layer, maybe you might have one half of the FFN and then the other half of the FFN. CP, what is CP again? Context parallelism, so one half of the input context, the other half of the input context. Pipeline parallelism, so the first layers and the last layers, and then data parallelism, which is like within the mini batch. Floating point 32, I thought they talk about this later on in the paper as well, but I thought it was interesting that they don't quite use low precision training. That's something that we saw a lot of people talking about, and there was some hype about it that maybe you don't need to be training at FP32, right? But I'm trying to find it here. This is a very long paper, so there's a lot of fucking shit in here. It's very hard to find. Yeah, here we go. This is more about inference, but in inference, maybe we should take a step back. What the fuck is FP8? What the fuck is FP32? Basically, these are data types. Data types is how much precision are you storing each parameter in. So those 405 billion parameters, each of those is being stored with a certain amount of little bits, right? Your little computer is effectively just storing a 1 or a 0. So how many of those are using? So for example, FP8, you could think of it like there's 8 little switches that it's using. It's more complicated than that because there's bits and bytes and whatever, but just think of it that way. FP8 compared to FP32, it's going to take 4 times as much little ones and zeros to store the 405 billion parameter model. So when you're doing inference, which means when you're actually using the model, quantization is very popular, where you take your model, all those 405 billion numbers, and you store and you use them at a lower precision data type, and it actually works kind of okay, and that's why it's really popular for inference. But when you're calculating gradients during training, using a high precision data type is a little bit more important because you really want the delta, that gradient, to be precise, right? But despite that, people have been training with lower precision data types, and I think some of these NVIDIA GPUs actually are designed for training at this kind of mixed precision training, I think it's called. So, damn, I'm just like not finding this here. But yeah, it was interesting to me that they didn't really necessarily use any fancy mixed precision. Like most of it is just FP32. Okay, let's go back here. collective communication. Our collective communication library for Llama 3 is based on a fork of NVIDIA's NCCL library called NCCLX. This is like, if you guys have ever done anything with GPUs at home, you've probably run into this NCCL library errors, which basically means that your NVIDIA driver is incorrect. There's something going on. But I thought it was interesting that they have a fork of that, right? So it's not even like, so NVIDIA is making the GPUs, and NVIDIA makes all the software to run stuff on those GPUs, right? Like CUDA is written by NVIDIA, NCCL is written by NVIDIA, but I thought it was interesting that the people at Meta are basically forking NVIDIA's code and writing their own improvements for that. So what that means is that NVIDIA isn't in as strong as a position as I guess you would want it to be in, right? Ideally, if you were an NVIDIA shareholder, right, you wouldn't want Meta to have to fork NVIDIA software to run their training jobs, right? Like, ideally, the story would just be like, hey, the NVIDIA software is so fucking good that we didn't have to change anything. And every time we asked for help, the NVIDIA people were right there, and they had engineers on site that were helping us with all. No. What the story that I'm seeing here is that Meta has a bunch of people on their payroll that are basically doing NVIDIA's job for them of solving all these low-level software issues of like running shit on the GPUs. So something to consider there, where I feel like if NVIDIA is willing to do that, then they're probably willing, or if Meta is willing to do this and have their own fork and maintain their own fork of NVIDIA's NCCL, I bet you they're probably willing to switch hardware providers, right? So I don't think they're necessarily going to stick with NVIDIA long term. I think that as you see more and more of these hardware providers come out, like Grok and maybe some other hardware providers, I think there's probably going to be a Chinese NVIDIA that comes up in the next 5 years. You might see NVIDIA lose market share as well. NVIDIA has always been garbage at compatibility. Sagar, is not backprop happening at FP32 always? Yeah, I think that's what they're saying here, is that they basically used FP32 for all gradient accumulation to ensure training convergence, right? So this is kind of what I was saying, where it's like, when you're training, you kind of really want to use a high precision data type because you're kind of changing weights ever so slightly, and like the value of the, like, so you want to be careful, especially for like momentum parameters in the optimizers as well. Like there's so many like weird little parameters like that where if you suddenly lose the precision on that, they just perform way worse. This was interesting here, this chart. So this is table 5, root cause categorization of unexpected interruptions during a 54-day period. So already they're letting you know unexpected during a 54-day period. So there was at least 54 days of training. So 54 days is not insignificant. We're talking about multiple months, and this is just one period. So this is probably even longer than that. So you can tell that the Llama 3 405 billion pre-training run took more than 54 days. But look at this. These are all the different problems that you run into where the GPUs just fail, right? Like if you have 16,000 GPUs, you're going to run into issues. I remember once I used to work at Amazon Robotics, and I was talking to kind of a more senior engineer there. And like he told me something which still sticks with me to this day. And he said, Hugo, there's problems that you run into with one robot, and then there's problems that you can only run into if you have 100 robots, and then there's problems that you can only run into when you have 1,000 robots. And I feel like that is exactly what I'm seeing here, right? Where if you just have one GPU at home, you're probably never going to run into some of these issues, like silent data corruption, right? But if you have literally tens of thousands of GPUs, you're going to be running into these issues every single fucking day, right? So think about it. Over 54 days, they had 148 GPU failures. So that's more than once per day. So the complexity of maintaining these large data centers is absolutely insane. And that's why I put a note here. Training data center is a new engineering specialization. So for the past couple decades, we saw how software engineering kind of became specialized, right? So because we had cell phones and then we had these social media apps and the internet, there was all kinds of specialized types of engineering that kind of developed for each of the specialized types of each of the problems that you run into when running a social media website at scale or doing something with cell phones, right? So like the same thing is happening here as well, where it used to be that machine learning, everybody in machine learning was kind of the same, like you're kind of doing the same shit, like, but nowadays you're seeing this specialization happening in machine learning where 5 years from now, you're going to have two different people that are both working in machine learning, but they're completely different type of people, right? Like one guy is like a theory math guy, and the other guy is going to be like a guy who knows all this data center, NCCL crap. So like, I think that as we're seeing a ton of money pour in and we're starting to see people run into all the different problems that you get whenever you try to do these things in the real world, you're going to start to see this kind of hyper specialization of engineering roles within these different organizations. And one of the new types of specialized engineers that I think is going to become extremely valuable, and maybe you guys should consider working towards this, because this is something that I think is going to pay very well. It's going to be this type of data center kind of like maintenance designing engineer, and like even going to the power consumption stuff that we were talking about, right? So now you're going to have people that understand the power consumption like behavior of GPU training workloads, right? Which I don't think exists now. There's probably only a handful of people that really understand that. So I don't know, AI is creating all kinds of new jobs. Failures in the GPU. They're mostly just talking about failures. Hardware issues may cause still functioning but slow stragglers that are hard to detect. Even a single straggler can slow down thousands of other GPUs, often appearing as functioning but slow communication. So that goes back to this chart here, which I think illustrates that perfectly, right? Where if you just have one GPU here that just takes a little second longer, and it's like, oh, it chokes on something, the CUDA kernel fails, and then it retries, and then it succeeds. The duration of that fail, retry, and then success, there's a bunch of other GPUs that are waiting for that. And then while that GPU is waiting for that, there's some other GPU that's waiting for that. So even just the tiniest little hiccup basically slows down your whole thing, because everything is so interconnected and everything is waiting for the output of the next thing. It's called chip design. Chip design is different than this. Chip design is yet another specialized, but chip design has been around for a while. I think there's chip design experts have been around for decades and decades. I'm talking about specifically this kind of like data center pre-training, like, I don't even know what to call them, but that's more the specialized engineer role that I see coming out of this. Okay. So that's a little bit about the data center. We're on page 14. We're roughly an hour in. I think we're going to have to blast a little bit faster here. Let's go into the training recipe. So there's 3 training stages here. We got initial pre-training, long context pre-training, and annealing. So cosine learning rate schedule, pretty standard, right? Lower batch size early in training. So early in training, you have a lower batch size and you also have a lower context size. Then you double the value. So you're increasing the batch over time during pre-training, and you're also increasing the context length over time. And you're also increasing the percentage of non-English data. So you're changing the data mix, you're changing the batch size, you're changing the learning rate, you're changing the context length. So there's a lot of things that are kind of changing over time as you do this pre-training, right? It's not just like you have one set of hyperparameters and then you just blast that for whatever 10 to the 28 flops they had. You're kind of the actual compute workload is changing as you go through the training process, the pre-training process, down to the data mixture as well, right? Which is actually important, because the data mixture is what you're putting in the fucking SSDs, right? So like the SSDs with your data set, if the data mixture was the same, then those never really need to change, right? You're just training for whatever 100 epochs of your data set over and over and over. It's the same data set over and over. But now the data mix is changing. So your data is changing, which means you're going to have to change that as well. So fairly complicated shit here. Increase the context length gradually in 6 stages, going all the way from 8K to 128K. Illustration of the overall post-training. So we had pre-training, right? That's the bulk of the training. And then you have this post-training, which used to be called the instruction tuning or RLH. Like there's a lot of words for that, but a lot of different terms for that. But the kind of umbrella term is just post-training, right? So once you've done the pre-training, then you're going to do the post-training. In the post-training, you have a couple different players here. You have something called a reward model, right? A reward model, this is basically like a reinforcement learning, you know, where you have your policy and you have your critic, right? Actor, critic. Like in a lot of reinforcement learning, you have this idea of like a model that tries to predict the reward, and then you have a model that actually tries to kind of predict the action. So like the reward model is really just telling you which, in this case, which output or which of the following, given the following input, which of the following outputs is the one that you want. And the way you train that is with this DPO, which is direct preference optimization, which is basically, you could think of it like PPO, but a little bit simpler. And it's what people are using now. I think they actually say that they tried PPO and that DPO was not only more efficient, but also better. Yeah, so we explored on-policy algorithms such as PPO, but found that DPO required less compute for large-scale models that perform better. So I think this is the nail in the coffin for PPO, which was fine because PPO is basically just the most basic RL algorithm. So for like, people were just using it just because they were afraid to try more complicated RL algorithms. But now the DPO is working better and requires less compute. I think everybody's going to use DPO if they're not already using DPO. The reward model trained on top of a pre-trained checkpoint using human annotated preference data. Right, so where is this human annotated preference data coming from? The human annotated preference data is coming from these annotators. So each preference ranking sample has 2 or 3 responses with a clear ranking: edited, chosen, and rejected. So you basically have these people that are sitting there that are basically not just saying I like version A better than version B, but they also edit. So now they can have a little bit more control. They can say, okay, I like A, but actually here's an even better version of A that I would have liked. Right, so you're seeing these in the post-training phase, the kind of annotation and involvement of these human annotators get more and more complicated. As you're spending more and more money on these foundation model trainings, right, the organization, the people ops is also getting more complicated as well, right? So like, it used to be like, okay, we just have like a team of like 3 guys over here and they're just sitting there like clicking A or B on these examples, and that's how we collect our human preference data. That's going to be more complicated, right? That's probably what people were doing 2 years ago. But now, okay, we have like a team of 100 people. They're using this very complicated internal tool where they can edit things and they can also do that. So I think this human preference data is just going to get even more involved and nuanced as we move forward, but hopefully we just eventually don't need that. I don't know. Synthetic data is a big part of this. Let's see. I'm kind of skimming through this, but it's very long. I would recommend the read, though. Statistics on human preference data. We ask annotators to perform multi-turn dialogues with the models and make comparisons among responses at each turn. We apply the above methods in 6 rounds. We collect new preference annotations in SFD, sampling synthetic data from our latest model. So they're using the synthetic data to generate more preference data. So this is actually very similar to what they did with the segment anything model. So Meta has been pioneering synthetic data for a while. The segment anything model was also trained with this kind of iterative approach as well, where they would use the checkpoint of the segmentation model to label more unlabeled images and then train on those unlabeled images and then get a new checkpoint and then do the same thing again. So this isn't new, this idea of kind of using like iteratively using the latest checkpoint to effectively create either synthetic preference data or label more images with more segmentations. So it's been happening for a while now. Rate the strength of their preference. So these annotators are basically choosing one of 4. So either way better, better, slightly better, or marginally better. Editing step after preference ranking to encourage annotators to further improve the preferred response. So not only are they picking which response they like better for this preference data, but they're also kind of editing the data. Kind of makes you think of like, who do they have doing this? Because this is getting kind of complicated, right? Like, are we really talking about like people in like the Philippines doing this? Because can people in the Philippines like give you edits on like some complicated like math? Like probably not, right? So like, who are these annotators? Because it's starting to get to the point where like you're going to need very high level annotators to like give good human preference data for arbitrary things. So as Llama 3 improves, we increase prompt complexity according to the target areas where the model lags. Do some rejection sampling using that reward model. See, most of our training data is model generated and requires careful cleaning and quality control, right? So if you're using the model to generate the outputs for this post-training, then you got to be careful, right? But unfortunately, it's kind of difficult to... The whole point of synthetic data and model generated data is that you can do it automatically, right? If you have to have a human read all your synthetically generated data, then what's the point? So they're going to be similar to how they had all these kind of automated data curation and cleaning methods for the pre-training phase. They're going to have a similar kind of data quality and data filtering pipeline for the synthetically generated data that they're using for the post-training. So for example, here they're filtering out any data that has overused phrases such as "I'm sorry" or "I apologize." So we're getting to the end of your LLMs telling you they're sorry because they're basically filtering that out of the preference data because they realize people hate that. Multidimensional curriculum learning. I think Tom is doing the annotations. Who's Tom? Do you know a meta annotator? We consider data that is the top quartile of RM scores. This is the reward model. So the reward model basically is filtering the responses as well. We prompted Llama 3 checkpoints so that the LLM is filtering its own data. We cluster complete dialogues, only keeping the ones that have a maximum cosine similarity less than a threshold to the example seen. So cosine similarity is a distance metric that you can use between vectors. Those vectors are basically representing the content of some text. So you have two pieces of text, you embed them into two vectors, you do the cosine similarity between those two, and if they're very similar, it means it's probably the same shit. So therefore you can filter out the ones that are the same. Coding. Which choice deserves time and effort? Master's degree in quantum computing or in AI? I think quantum computing is more risk but more reward, right? So the problem with quantum computing is it doesn't really work that well. So it's a very small pool of jobs, and there's a chance that you join and that nothing happens for 10 years. But if you get a master's degree in quantum computing and everybody else is working in AI, and now all of a sudden quantum computers work and you're one of 100 people that knows about quantum computers, you're going to become very valuable very quickly. So it depends on kind of your appetite for risk and like how okay you are kind of working on something that's a little bit off to the side and not as cool. But I don't know. I think that's up to you whether you work on quantum computers or just kind of more of this type of stuff. High priority programming languages, Python. All the Python people in the chat, you know, I feel like I'm a Python first kind of guy, so I like seeing that. Python is the highest priority programming language. They train a code expert by branching the main pre-training run and continuing pre-training on a 1 trillion token mix of mostly code data. So this is kind of interesting because it means to me that they had to basically fine-tune. So what they're doing here, it's still part of pre-training, but I would consider this kind of fine-tuning, where you're taking your pre-trained model and then you're now deciding to do a little bit more pre-training on code-specific data, right? So I would think that's kind of old school, right? This old school mentality of like, hey, if we want to have... we want to take this pre-trained image model and then fine-tune it for this specific application, then fine-tune it for this specific application, then fine-tune it for this specific application, right? So this is kind of the same idea where they're saying, okay, let's take the generic Llama 3 and then we're going to basically now have a branch. We're going to branch that and do a little bit more pre-training and then the post-training, but specifically for code. And then we're going to have probably a medical version. So I don't like that. I don't like this idea of expert training. I think that you just got to bite the bullet. And at the end of the day, there's going to be the foundation model should be good enough at all these tasks that you shouldn't need to have to train special experts for different tasks. But if you really want to push the the boundaries on these benchmarks, which I think is existential for this, right? If you're meta, what you really want to do, this is the most important thing that you want. You want to be able to beat these models on these benchmarks. So training code experts so that you can juice out the code benchmarks, and training medical experts so you can juice out the medical benchmarks. Like, that's more important than having one model that can do everything. But I think from kind of an AGI, ASI kind of point of view, having one model that can do everything is a little bit more interesting. Okay, we were here. Synthetic data. Yeah, okay, so synthetic data is even more important and useful for domains where you can verify the output, right? So I like to say that AlphaGo was able to achieve superhuman Go performance by generating synthetic data sets of master level Go play, right? So there's a very small data set of master level Go games because there's a very small amount of master Go players. So how are you going to train a model when there's only a small amount of master Go data? Well, you need to generate more of that master Go data. So how do you generate more master Go data? Well, you just literally have a model play itself at a high level, and there you go. You just created one more data point that is a high level Go game. So that only works because you can verify at the end, okay, this guy won and this guy failed, right? So synthetic data works well in these type of environments where you can heuristically verify whether the solution is correct. And for something like code, this is a perfect match, right? For something like math, this is a perfect match because you can always verify. And this is why we're seeing progress in coding and progress in math, right? We saw the news that came out earlier this week about the models. I think it was a DeepMind model getting silver in the International Math Olympiad. Like, why are we seeing superhuman math performance and superhuman code performance kind of emerge first? It's because you can create synthetic data for that. So synthetic data generation offers a complementary approach at a lower cost and higher scale, unconstrained by the expertise level of annotators. We use Llama 3 and the Code Expert to generate large quantity of synthetic supervised fine-tuning dialogues, aka here's some fake little LeetCode problem. Oh, boom, here's a solution to that. Is that the actual correct solution? I don't know. Let's plug it into an interpreter. We do it. Oh, it actually works. Okay, then actually use that. If we plug it into an interpreter and it doesn't work, okay, well, don't train on that because that's bad, right? So you can filter the synthetically generated examples for code, but you can't quite filter it for, I don't know, like, what's something where you couldn't really generate synthetic data for? Philosophy, right? There really isn't like a heuristic way to evaluate philosophy statements, right? So it'd be basically impossible to synthetically generate high quality philosophy arguments, but it's easy to generate code because you can always verify whether that code. We introduce execution feedback as a code of truth, enabling the model to learn from its mistakes and stay on track. Adding general rules of good programming to the prompt improves the generated solution quality. So there's a little hot tip for you guys using LLMs as part of your coding workflow. If you add some general rules of good programming, so I guess if you copy paste some text there into your context about like what makes a good Python code, it actually helps it solve it. So it's kind of similar to the chain of thought. We run all generated code through a parser and a linter, prompt the model to generate unit tests, execute in a containerized environment, aka a Docker container, catching runtime execution errors. When a solution fails at any step, we prompt the model to revise it. The fine-tuning process is conducted over multiple rounds with each round building on the previous run. After each round, the model is improved, generating higher quality synthetic data for the next round. Here's your self-improvement flywheel that is going to get us to ASI. So much like we got to superhuman Go, we're going to get to superhuman code and superhuman math because we're going to be able to create these self-play loops effectively. Performance gap between most major programming languages such as Python and less common ones like PHP. So they can supplement the existing training data by translating Python examples into PHP examples, which I thought was kind of cool. Over 1.2 million synthetic examples. We utilize the model as a judge, where earlier versions of the Llama 3 assess and assign a binary based on two criteria, code correctness and code style. So it's kind of like a reward model kind of mindset. The model is its own reward model. Here's the languages they use for the multilinguality. Interestingly, they don't have Chinese on here. I thought that was weird, right? I think English, Spanish, Hindi, like those make a ton of sense. Those are some of the most popular languages, but you have Portuguese, but you don't have Chinese? Like, what the fuck? I guess it's that Meta doesn't have any products in China, right? Like, they literally aren't allowed to operate in China, so they were just like, you know what? Fuck you. If you're not gonna let us have Instagram in China and have Facebook in China, then we're not gonna even train our foundation model in Chinese. Yeah, it was kind of like Thai. Like, I think Thailand actually has a pretty big population. What is the population of Thailand? 70 million? 98 million in Vietnamese. Like, look at that. 98 million. There's way more Vietnamese people than there are Thai people, but for some reason they chose Thai. I guess it's just, I don't know. Meta has all kinds of internal metrics. I'm sure they know the amount of Facebook users in Thailand versus the amount of Facebook users in Vietnam, and it might be the case that there's a hell of a lot more Facebook users in Thailand for some reason that I don't understand. We train a multilingual expert by branching off the pre-training run and continuing to pre-train on a data mix that consists of 90% multilingual tokens. So kind of a similar story to the code, right? Where the code did the same thing. They trained a code expert. So they kind of did like a fine-tuned code version of the Llama. And then they also did a fine-tuned multi-language version. And some people might be annoyed that I'm using the term fine-tuning there, because really it's still pre-training. So even though it's a branched run, it still pre-trains more. But like kind of from a more classic deep learning mindset, this is fine-tuning, right? It's like you're taking something that's trained on a general thing and then you're kind of training it on a more specific thing. And to me, that's kind of the high-level definition of fine-tuning, is like going from something more generic into something more specific. So that kind of specialization. But here they're calling it expert training. When they generate the synthetic data, they're generating at a temperature of 0.2 and 1, or 0.2 to 1, specifically at 0.6. Lack of ground truth chain of thought. There's often a shortage of ground truth chains of thought, specifically in math. So they use model generated train of thoughts, but the problem is sometimes those intermediate steps are not correct. So they have the model filter through that. Enhancing models to utilize external tools such as code interpreters allows them to reason by interleaving code and text. I think this is powerful. So tools comes from the paper tool former, right? Where we realize that these language models can actually zero shot tools, which are basically like an API. Like you give it a little calculator API where it can say, calculator 1 + 1, and then it'll actually use a calculator to do 1 + 1. And this is probably the way that we're going with AI, right? Where for a moment we thought that maybe these AIs are just going to be so smart that they're just going to be literally know the answer to all these things. They're going to store all the knowledge explicitly within their weights. But I think more and more people are realizing that you can separate kind of like knowledge and like pure like addition, division, like kind of things like that away from reasoning. So we're going to have a much smaller model that does all the reasoning, and it just knows how to use external tools such as a calculator, such as I think they actually get it to use Wolfram, which is kind of cool. Let's see if they talk about so they have Brave Search. So Brave is kind of like a browser, kind of like Chrome. So Brave Search is basically going and using a search engine. They have a Python interpreter, so the model can basically generate and execute code to perform complex computations, reads files, solve tasks, blah, blah, blah. And then Llama 3 can also use the Wolfram Alpha API. The Wolfram Alpha API is basically, it's like a very fancy calculator, right, that can do more fancy things. But I feel like Wolfram Alpha API and Python interpreter are kind of similar. I feel like there's a lot of overlap there, so I'm kind of curious why they got both of those on that. But I guess the Wolfram database, maybe that's really what they want it for. The Wolfram database probably has all the weird shit like what is the atomic weight of cesium, right? Like that's probably in the Wolfram database. So that's something that you don't want the model to like just memorize the atomic weight of cesium. You'd rather it just be like, oh, you want the atomic weight of something? Okay, I know how to use the Wolfram API to say, what is the atomic weight of cesium? And then there's some specific hard-coded answer there, and I just pull it from there, right? So I can reduce, I can free up some of the model capacity that I would have wasted memorizing that little factoid and use that model capacity for kind of just general reasoning and knowing when to use those tools. All right, let me take a little sip here. I think we're still talking about coding. Yeah, we were talking about here. All right. We identify mathematical skills where the model underperforms and actively source prompts from humans to teach models those skills. So this is kind of interesting because to me, it tells me that Meta is already looking at human experts. So this is something that we saw even at OpenAI, right? OpenAI had some job postings where they were like, hey, if you're an expert at some weird fucking niche thing, like in this case, math, we will hire you to generate training data for our math model, right? And I think that this is going to be more and more of a trend, and it's actually going to become a thing for robots as well, right? I think that at some point, the limiting factor for humanoid robots is they're going to be like, well, where we can get fucking like steak cooking data. Okay, well, why don't we just get a bunch of professional chefs to come in here and put on a mocap suit and sit here and cook steaks for us, and then eventually we just have enough steak cooking data that a robot can learn how to cook steak. So all these specialized human skills, people are going to eventually pay you to teach an AI how to do that skill. So I don't know. I think this little sentence here lets you know kind of where society is going and maybe what some of the jobs of the future are going to be. We train outcome and stepwise reward models, filter the training data. We use MCTS. We've seen MCTS in a bunch of these synthetic data papers. We read other synthetic data papers where they do this, right? They let the model kind of roll out a bunch of, basically expand this tree, right? And like, why is it a tree? Well, because when you auto-regressively produce the next token, there's a couple other tokens that could have also been outputted. And then if those tokens were outputted, then there could have been a different token. So it's like every single token that you output is like really the beginning of this branch that goes out where you have all the possible answers. And you can, what MCTS does is you're basically saying, okay, let's go through let's create this tree, and then we can search this tree with our reward model and figure out which specific path or branch down that tree is the best one. So being a little bit more explicit about like, okay, what is the tree from here? Searching within that tree and then finding the best path. And all the chess AIs and Go AIs do this, right? They're doing some kind of MCTS with a reward model that's kind of like going through every single trace in this tree, every single branch, and then figuring out the best path from there. And humans do that as well, right? So like, actually, I don't even know. I don't know enough about high-level chess. I think they play a little bit more instinctually, but like when I play chess, at least because I suck, I'm thinking about, okay, if I do this and then they do that and then they do that, then I do this, right? So like, what am I doing there? I'm building this tree in my head. So explicitly building that tree and searching through that tree is a very good way to reason. Code execution is used as feedback signal to eliminate cases where the reasoning chain was not valid. Yeah, so much like you need that ability to heuristically evaluate to generate synthetic data that is of high quality, you also need to do that for chain of thought. It is largely impractical to get humans to annotate such examples due to the tedious and time-consuming nature of reading lengthy context, so we predominantly rely on synthetic data to fill this gap. We're getting there, guys. If you have 128K contexts, good luck trying to get some random guy from the Philippines to read that, you know? So we're getting to the point where like creating the SFT data sets for these long context models is like beyond the abilities of humans. So we literally have to rely on these models to produce it for them. Long context code reasoning. I thought this was interesting. So most of the coding stuff that we see with models, like all of these coding benchmarks here, for example, human eval, MBPP eval plus, like these are kind of like leak codes, you know, they're like little problems where like the problem is like a paragraph and then the answer is like a little tiny function with maybe like 20 lines max, right? So all the coding that we've seen up until now is basically very small little snippets, right? But in practice, when you're actually writing code at a company, the code base is usually much bigger, much more complicated. So we want to start creating examples of code that are more have basically bigger context. And the way that they do that is they do this kind of thing that I'm calling code base masking, where they have this large set of files, and those files might all import one other file. So then they delete that other file or they mask it, and then they basically get the model to say, okay, here's the whatever maybe not 1 million, but like here's 10,000 lines of code, and we removed 5,000 lines of code, and then generate the missing code. So it's kind of like the same way that you would do masked, like you would take a whole image and then you mask out certain chunks of certain patches of the image, and then you get the model to reconstruct those patches. And that's a very common self-supervised learning strategy. They're kind of doing the same thing for long context code reasoning, where, hey, let's just get these larger code bases, we just remove parts of it, and then we get the model to replace that missing part, and then boom, here we go. Now we have this way of creating examples of long context code reasoning. Like a Star Trek replicator, I guess. Okay. Teaching LLMs to use tools such as search engines or code interpreters hugely expands the range of tasks they can solve, transforming them from pure chat models into more general assistants. Yeah, I'm a huge proponent of this, right? I think that that's a really clever solution to get around the fact that these models have this hallucination problem, right? Where the best way to solve the hallucination problem is to get them to just use tools, which is exactly what we do, right? It's like even a professional mathematician like isn't doing like, maybe they are, but they aren't like multiplying big numbers in their head and like dividing big, they're just using a calculator, right? So like, I think it's kind of creepy that AIs are going to be using tools the same way that humans use tools. It kind of makes you realize that these AIs are kind of more human-like than we think they are, but I think it's a good solution. We implement our core tools as Python objects. The Python supremacy continues, converting function definitions and calls to a JSON format. So this is kind of what you see out of the OpenAI tool API, the Gemini tool API, like all of these different model tool APIs, they're all starting to converge onto this standard format. So maybe in the future, all LLMs will use Python, because that just ended up being the easiest way to do tool calling. So I don't know, attempt to buy stock in Python, even though I don't think you can buy stock in Python, but Python is like by far the closest programming language to English. And I think that's why it's such a popular language. And I think that's why it's going to become the popular language for LLMs as well, because LLMs are very good at English. They do some human feedback and annotation for the actual tool calling as well. So I thought that was kind of interesting, especially when they have multiple tool calls. So the basic form of tool calling is you have your system prompt, then your user prompt, then the LLM says, okay, now I need to do this tool call. Now I actually get the tool call back, which is the tool output, and then I read that, and then this is the context which I use to create the final answer, right? And the user only sees, it doesn't see this. The user doesn't see the tool call or the tool output. But in a multi-step tool use, you have more tool calls, more interweaved. So they have basically human annotated supervised fine-tuning data for multi-use or multi-step tool use. Here's all the different file types that it supports: TXT, PDF, PowerPoint, XLSX, CSV, JSON, JSON-L, HTML, XML. There's a very clear lack of YAML there. So JSON wins over YAML, I suppose. All right. We augment our synthetic data with different prompts to teach the model to use tools only when activated. So a little bit of data augmentation on the system prompt. Okay. Here's I think now there's like a section here where they talk about the kind of like the safety crap, but I'm not super interested in that. Steerability. Here's a new definition for you guys. Steerability is the ability to direct the model's actions and outcomes to meet developer and user specifications. As Llama 3 is a generic foundation model, should be maximally steerable to different downstream uses. So you should be able to basically get it to do anything. Here's the benchmarks. We kind of already went over those. A lot of these benchmarks, like we said, are basically kind of cheated. You know, they are using few shots, confidence intervals, like they're basically sampling multiple times. They're letting do chain of thought. So like, don't read too much into these benchmarks. And as they say here, common sense benchmarks are likely saturated. We need new benchmarks. Model robustness, math and code. Oh yeah, this right here, this was fucking weird. Label variance. We study the model response to different choice token sets. So whenever they ask the model a question, right, and there's 4 answers, there's A, B, C, and D. They were like, hey, what if we change that? What if rather than saying, here's a question, and then is it A, B, C, or D? And then is it A with parentheses or A with a dot or 1, 2, 3, 4? And then they tried something different. They're like, okay, rather than A, B, C, and D, what if we use 4 kind of weird tokens that are really not associated with these questions? So like OE, whatever the fuck this is, the backward 3, and then the umlaut. And they're like, okay, it's the same question. It's the same benchmark with the same questions. But now rather than saying here's option A, B, C, and D, it's option OE, option whatever this is, option backwards 3. And I'm like, what? And then look at this. The accuracy is like significantly worse. And it's not even with just the little model, right? It's not even just the little model. Like, look at this. It goes from 65% accuracy to 50% accuracy. The big model goes from 65% accuracy all the way down to like look at that, 85% down to 65%. It's the same fucking question, the same answers, but now rather than saying A, B, C, and D, you're using these weird rare tokens. And I love that. I love that just because it's so weird, right? It's like it just really lets you know how weird these models are, where what's probably happening is that whenever it sees A, B, C, and D, it probably puts the model into this like, oh, I'm taking a test. I'm taking a test, therefore there's one of these answers that's correct. So it's like just changing some of the tokens around completely fucks the score, which to me just lets you know how fragile these models are and how fragile these benchmarks are, right? Where it's like, it's really not reasoning which answer it's the best. It's like, it's kind of like weirdly just like picking, I don't know, something to consider. I thought this was a weird little quirk. Question by RandomBot44. What cursor theme is that? I don't actually know. I just kind of picked a big cursor because I used to not have this big cursor, and then I watched some of my videos, and I like to like wave at things like this, and I was like, I can't see my fucking cursor at all. Like nobody can actually see what I'm waving at. So I was like, I need to make the cursor way bigger and way more obvious so that people can see my cursor, especially because I tend to like wave at things and like hover over things. So that's why I have this really big blue cursor. So it doesn't make me any faster at coding. It doesn't improve my ability to operate a computer in any way. It's just literally big so that you guys can see it. The answer order is also important, but that's something that we've seen before. Adversarial versus non-adversarial contamination analysis. To estimate to what extent benchmark scores may be influenced by contamination of evaluation data in the pre-training corpus. This is another thing that people have noted as well, and this is not the first time people mention this, but a lot of these benchmarks exist in the pre-training corpus, so you're literally training on the benchmark. So you're not really testing your model's ability to reason, you're testing your model's ability to memorize. So another reason so as to not trust these benchmarks. For example, HelloSwag. Basically, you should never trust HelloSwag because the contamination is high. Post-training. More benchmark stuff, more benchmark stuff. Where are we at? We're at 36. Almost there, almost halfway. More benchmark. Coding benchmarks. $72, $40. 67, $32. $60, $42. Mistral is looking terrible, guys. What do you do if you're Mistral? You know, you're hanging out in Paris. You're probably barely working, you know. Definitely not 997 in fucking Paris or 996. You're working like 428 or something. I don't even know. Like, you're basically just not working. You're eating croissants and getting paid $1 million salary to create a foundation model that is absolutely shitting the bed against Llama 3. So a lot of these companies that are foundation model companies, I don't know what they're going to be doing here, you know. Meta kind of just is not just destroying OpenAI and Anthropic, but it's also destroying like the long tail of these little startups like Mistral and Mistral. It's going to be very hard for them to raise money if they can't beat the benchmarks. So they're probably in full panic mode. Here's the performance on different programming languages here. Look at this C# compared to C++. This is weird because C# is easier than C++. C# is what you use in Unity. So this is actually kind of weird because maybe it's just because the problems are simple. So it's like if it's the same simple problem, but like you can do like CPP can get way more complicated than C#. So like it's probably just the problems are simple. I don't know. Llama 405 is the best in its category on ARC-C. ARC is probably the best thing we can get to an AGI benchmark, to be honest. It'll eventually get solved, but I think right now I trust ARC score more than I trust a bunch of these other scores. Human evaluations. So this is where they get people to look and say, okay, which one is better? And I'm just going to cut to the chase because what they end up determining here is the kind of summary. On nearly all capabilities, the win rate of Llama 3 and GPT-4 are within the margin of error. So Llama 3 is effectively GPT-4. On multi-turn reasoning and coding, Llama 3 outperforms GPT-4, but it underperforms GPT-4 on multilingual prompts. Okay, so basically human evaluation, which is what the ARENA scores are, right? So people like to mention the ARENA score, which is like people go and they look at two different answers. We're basically on par. Llama 3 is GPT-4. All right, and then there's the big section on safety, which I'm going to skip because I think safety is a bunch of bullshit. But blah, 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 here, false refusal. I think they actually release it as a separate model. So they have the base model, which they have the pre-trained, then they have the code version of it, the code expert, they have the multilingual expert, and then they have the post-training, supervised fine-tuning, DPO on all three of those. And then there's a separate additional model, which is kind of like the filter model. That's kind of the way I understood it. But I honestly didn't really read this section here. But I do like that they kind of did the separate model, which means you should be able to just turn it off. Cybersecurity, blah, blah, blah. As you can tell, I kind of started losing interest at this point in the paper. Red teaming, blah, blah, blah. Red teaming. Input, there we go. Llama Guard, that's what I wanted to say. Yeah, so they have a model which they call the Llama Guard that basically, it's like a classifier. Okay, inference, here we go. This is more interesting. We investigate two main techniques to make inference with the model efficient: pipeline parallelism and FP8 quantization. So pipeline parallelism, again, is whenever you basically have different GPUs that are doing different parts of the model. So you might have one GPU doing the beginning, one GPU doing the middle layers, and then one GPU doing the last layers, right? In this case, you have 8 NVIDIA H100s in one server node, but it doesn't even fit in one server node. Look at this. Llama 3 405B does not fit in the GPU memory of a single machine with 8 NVIDIA H100s. Like, what? That seems like such a bad design. Even at BF16, BF is Brain Float 16, which is like a special type of Float 16 that Google came up with. So they literally have to parallelize the model inference using BF16 across 2 of these server nodes, so 16 GPUs in total. Within each machine, so within 8 of the GPUs on a single machine, you have this NVLink, but then within those 2 machines, you're going to have a slower communication overhead, so it can kind of get a little bit fucked there. And here are the charts to kind of show you that. Effective micro-batching on inference throughput and latency. So you see here different BF16s, BF16 plus micro-batching, prefill latency, time to first token, time to incremental token. This is interesting because these are metrics that we're probably going to see start to become important, right? As you have a bunch of users interacting with these LLMs, one of the more important metrics that you kind of want to look at is time to first token and time to incremental token, right? It's like, how long does it take for your system to respond to the user, right? You really don't want, especially if you're using this pipeline parallelism where you're kind of like splitting the whole model across multiple GPUs, like, and then that also gets complicated depending on how batched your inferences, right? It's like, it's not just one user interacting with the model. You have a lot of user requests all coming in at the same time. How long is each individual user waiting, right? And we saw some fancy shit that people were doing with LoRa's. I think there was a paper we read called S-LoRa or something like that, where you have a GPU or a server rack with 8 GPUs, a server node with 8 GPUs, and then different GPUs have different LoRa's, and they're kind of loading those LoRa's in and out so that you can basically serve a variety of different LoRa's for a variety of different user requests that are all coming in kind of batches. But it's kind of the same way that training is getting all this complexity, and kind of all these different tricks are emerging to improve the kind of pre-training. The same thing is happening with inference, right? Where you're going to have, it's a completely different type of workload, right? Because in one, you have basically these giant batches and all the GPUs are kind of working in sync. That's the pre-training. But then inference, you have this user requests that are coming in at different times, and there's probably specific times of the day where more user requests comes, and then times when it goes down. So like different problems, which are going to require different solutions. They quantize to FP8, leveraging the native FP8 support of H100s to perform low precision inference. This is kind of cool, and it definitely broke some of my mental model. In my mental model, I was thinking, okay, people use NVIDIA GPUs for training, and then they use something like Grok for inference. But here, they're using NVIDIA GPUs for inference as well. So I wonder if NVIDIA is going to have a different line of GPUs for inference and then a GPU for training, or whether they're just going to continue to have the same GPU for inference and training. I think it makes sense for them to split for those 2 different use cases there. We quantize most parameters and activations in the feed-forward network layers, which account for roughly 50% of the inference compute time, and we do not quantize parameters in the self-attention layer of the model. So they're not, they're using different mixed precision quantization inference. We do not perform quantization on the first and last transformer layers. This is what I was trying to find earlier. Tensor-wise and row-wise FP8 quantization. So here's your input, your user, or the input from the previous layer, coming in at BF16. Scaling factor weight, BF16 weight quantized. I don't exactly know what they're trying to say here. Because with the quantization, right? When we read quantization papers, there was a bunch of work by the Tim Detmer guy. He has a bunch of interesting quantization papers, but there's this interesting dynamic in these models where like a lot of the model weights like don't matter, and then there's basically these outliers, right? There's like specific some activations are way bigger than the other ones. So it's like there's kind of like this inherent sparsity to like these large deep learning models, and identifying which things don't matter, which things matter, which things you can quantize, and which things you should keep at a higher precision. You know, you kind of got to know what you're doing there. Dude, I'm starting to lose steam here. Where are we at? 12:01. A little bit over 2 hours. We're on page 53. All right, let's go. FP8 inference performs on par with BF16 even without these mitigations, which is why I think you're going to see separate hardware. I think training you can't quantize as well as inference. So if you can design a GPU that you know is going to have like FP8 or even like the ternary byte, I think it's like the 1.58 bit quantization or whatever the fuck it is, like super quantized. Like imagine designing a GPU specifically for inference where every single memory cache in that GPU is only accepts extremely small data types, right? The inference you can get from that is going to be so much better than the inference that you can get from a training GPU where everything is designed for BF16s. So this is the fact that quantization works so well for inference but so poorly for training, I think is why you're going to see this bifurcation in training hardware between training and inference hardware. Throughput latency trade-off in FP8 inference. Prefill throughput, tokens per second. Prefill latency. So prefill is you type in your whole paragraph of context and it needs to basically mash that through the transformer. And then decode, this is the autoregressive, like one token at a time, right? So you can see just how much slower that is. FP8 fits in one node. Ah, you see? If you use it, so what they were saying up here, you see, BF16 doesn't fit on a single server node, so you need 2 GPU nodes, or 2 server nodes, 16 GPUs total. But if you quantize down to FP8, then it fits on a single node, right? And because communication within the node is much faster than communication across 2 nodes, if you can fit it all on one node with FP8, you get roughly twice the throughput. So that really is letting you know that even though the FP8, you're going to get a little bit worse accuracy than this BF16, it's totally worth the 2x throughput. All right, and that is the end of the inference, and now we're going to get into the experimental part. So in the beginning of this paper, they talked about how this isn't a multimodal model, right? I bet you they tried to make it multimodal, but it didn't quite work well, so they just released the language model itself, and then they do some experiments where they try to basically use a pre-trained image encoder and a pre-trained speech encoder, and then just kind of glue it the same way that we see most vision language models nowadays. You know, like the Llama model was probably the first and the most famous one of these, where you basically just take the output of a clip encoder and then using a little adapter, connect it to a language model, and then just kind of use that. And it kind of seems to work pretty well. That's how most vision language models work nowadays. Image data, trained on image text pairs. What are they using as the image encoder? Do they tell you? Deduplication. Okay, here's your image. You see this image patches. That means that it's a VIT. So as soon as you see image patches, you know it's not a ConvNet. You know it's a VIT image encoder. Compositional approach to adding multimodal abilities. Video is just a sequence of image patches. You're just adding the time dimension to the image. Here's your linear transform image encoder. There we go. Confirmed. Image encoder is a vision transformer because you see here, here's the transformer block. Now, here's the different representation, or what they call the adapter or connector. Sometimes it's also called in different papers, right? It's the thing that's connecting your image encoder to your language model. So this thing here, this is the actual Llama 3, right? But they need to figure out how to connect the Llama 3 to, or adapt it to the output of this image encoder. And a lot of times the tokens that come out of this, or the tokens that come out of the adapter of this image encoder kind of stack here, or image backbone, like they're going to be kind of like interleaved with the text tokens, right? That's something that we're seeing where in a very simple case, you just have all the image tokens, then you have all the text tokens, and then the model just outputs text tokens. But we saw in the Chameleon paper by Meta that they were doing much more fancy shit, right? They were literally interleaving these image tokens and text tokens, and the output itself could also be interleaved image and text. So it could literally generate text and then generate an image and then generate more text, which that's why I think the Chameleon paper is more representative of what we're going to see in the future. This is kind of more kind of what we've seen in the past. To further improve our image text data, we extract text written in the image and concatenate with the caption. That written text is extracted using proprietary OCR. So some kind of old school OCR pipeline. They use it to basically augment the labels of the images. Seems like a smart move. I'm like scanning this for the first time as well. I didn't get the opportunity to read this part. Boom, here you go. Clip. So clip is the image encoder, which we could have probably guessed. The other one would have probably been Dino. Around 6 billion image text pairs. 336 by 336. It's kind of actually small. We resize all images to at most 4 tiles. Yeah, so this is another thing. We've seen this in pretty much all the VLM papers where if you have an image that's too big, they'll cut it into these tiles and then feed each tile separately into the image encoder. And then in that way, you don't lose any information, because sometimes if you take a big image and you kind of resize it to a small image, you'll lose the text. So this is splitting it up into these tiles and then feeding each tile separately into the image encoder is pretty popular. They interpolate, of course, for video. You're not going to feed every single frame, so you're kind of like picking some subset of frames over time. VIT image encoder. Pipeline parallelism. Yeah, that makes sense, right? So one GPU is probably going to have the image encoder, and then maybe the other GPUs have the LLM, right? So like you're separating the model, or you're doing parallelism over the whole model, right? So like the benefit of that is that you can split a big model over a bunch of GPUs, but the negative of that is that now your other GPUs are going to have to wait for this first GPU to do the image encoding. More computation is performed on some tokens than other. Image tokens are processed by the image encoder and the cross-attention layers, whereas text tokens are only processed by the language backbone. Yeah, so here what they're saying is that you have some question or prompt, right? You're putting in an image and then you put in text. The image has to go through this whole stack here, right? It has to go through the image backbone, versus the text is just going straight into the LLM. So you have to kind of wait for all the image tokens to process before you can process the text tokens. So, you know, waiting on the weakest link in the chain, which happens in pretty much all cases with these parallelism strategies. We find that performing gradient accumulation in BF16 led to numerical instabilities. We addressed this by performing gradient accumulation in FP32. So no mixed precision training for the multimodal model. Everything in FP32. Post-training. We convert a highly filtered collection of existing academic datasets into question-answer pairs using templates or via LLM rewriting. So the LLM is not necessarily creating the data synthetically, but it's augmenting the data. So kind of like how you flip images left and right and corrupt them and stuff like that type of augmentation in image space. You can do a similar kind of augmentation in text space where you're just kind of changing the prompt a little bit, changing the answers a little bit, and you can just do that with an LLM. Utilize the reasoning capabilities of text input LLMs to generate question-answer pairs in the text domain, and then replace the text representation with just corresponding images to produce synthetic multimodal data. I wonder, this is like basically what other people do as well, right? Like, I don't know if I would call it technically it's synthetic, right? So like if you are training a vision language model and you're using GPT-4V to take an image caption pair and then convert that image caption pair into an image paragraph pair, right? So like rather than just like a little tiny image caption, now it's like a whole paragraph, and you're using a pre-trained vision language model like GPT-4V to do that. In a way, that's you're creating a synthetic data set, right? Because your data set is no longer the actual caption that some human came up with to that image. It's now some synthetic caption, which is generated by a different vision language model, and then you're using that to train your own vision language model. So the definition of synthetic data is quite broad and encompasses most things. Can you use Dino when it's not trained with text? Yeah, Dino is an image encoder, right? So really all it's doing is it's taking your image and is turning it into some vector that represents that image. When you're using Clip as an image encoder, it's doing the same thing, but the difference between Dino and Clip is that Clip has been trained in such a way that the representation that it creates of that image has been aligned via contrastive learning to the representation of the text. So whenever you feed an image into Clip, the representation is more semantic-y, even though that's not really a word. Compared to Dino, the representation might be a little bit stranger, right? Not like as text-like, but both of them are pretty good. And actually, if you use them in combination, they're even better. DPO, rejection sampling. Quality tuning. We curate a small but highly selective SFT datasets where all samples have been rewritten and verified by humans or models to meet the highest standards. We train DPO models with this data to improve response quality, calling the process quality tuning. QT significantly improves human evaluations without affecting generalizations. So it's like the whole curriculum is getting increasingly complicated, right? We were already changing the pre-training mix over the course of pre-training, and now you have various rounds of post-training SFT and DPO that are being done with different quality or different levels of quality, where even within those, some of that is being synthetically generated and augmented and then evaluated by human annotators. So like this whole pipeline is quite complicated, to be honest. But if you got a ton of money like Meta, why not? Some video recognition results. Speech experiments. Use your speech encoder. Speech understanding. You're turning this into some kind of speech tokens. Where's the adapter? There should be some kind of adapter. Oh, here it is. There it is. Speech adapter. Speech encoder outputs some representation of the speech. Speech adapter turns it into tokens. Then Llama 3, you're going to need to fine tune it a little bit so that it can consume those. Our automatic speech recognition training data consists of 230K hours of manually transcribed speech recordings that span 34 languages. 34 languages, but your model was really only trained with like 8. That's kind of weird. Speech encoder is a conformer model with about 1B parameters. Mel spectrogram features. Yeah, so it's like this ComNet with rotary attention. It kind of seems like an afterthought. Like, honestly, it seems like the image and speech modalities here are kind of a bit of an afterthought. Text normalization. Speech generation, speech understanding results. Ooh, it's better than Whisper. Word error rate. But there's so many different versions of Whisper. What is this? Is this Whisper V2? I think there's even newer ones as well. And a lot of the worst Whisper versions that you use are like quantized, kind of distilled, tiny versions as well. So like, who's actually using the OG Whisper? All right, we're almost there, dude. The related work section. There's a bunch of papers. Everybody getting their citations. This is citation orgy. Look at all these citations. Conclusion. All right, guys, we made it. We made it. Look at all these people that worked on this. Holy shit. Oh my God, dude. Mark Zuck. The Zuck God, dude. He's not even on the core contributors. He's just on the thank you page. All right, let's read this conclusion. In many ways, the development of high-quality foundation models is still in its infancy. I agree with that. Our experience suggests that substantial further improvements is on the horizon. I don't know about that. I think that the language models are kind of capping out. Like we were kind of seeing, I think they were really, this chart made a good point right here that it's an S curve, right? We're kind of getting to the top of this S curve of the language model itself. I think if we really want to go further, it's got to be multimodal. It's got to be some kind of new architecture. There needs to be something different that I think gets us to the next S curve, right? And what I mean by that, I bring this up all the time, but technology is S curves. Yeah, where it's like technology is like this, right? It's like you reach the limit of one technology, which is an S curve, and then you find a new S curve to go to the second limit, right? And I feel like, to me, large language models, we've kind of capped them out. We're kind of at the top, right? Which is really what they're doing. And we need to find the next S curve. So I kind of disagree with a little that second sentence here. We found that strong focus on high quality data, scale, and simplicity. Yep, I agree with that. We explored more complex model architectures and training recipes, but did not find the benefits of such approaches to outweigh the additional complexity. Yes, good. The simpler it is, the better it is. Developing a flagship involves overcoming a plethora. They use this word like 7 times in this fucking paper, and it's kind of annoying. Plethora, look at that. Like, come on, dude. Deep technical problems, but also require clever organizational. Our pre-training data was procured and processed by a separate team that was strongly incentivized to prevent contamination with external benchmarks. Also, because it keeps the... This is a little bit of double speech here, right? As we were saying before, there's a huge kind of legal risk to admitting that you're pre-training on a bunch of private data. So by keeping the data team separate, right, by having this clever organizational decision of keeping the training team separate, you can have those people sign NDAs, and then the people that work on all the other shit, they're not even aware that the data team is using the like private Facebook data or something like that, right? So like, I think this is also kind of like a a need to know, kind of like what the government does with like secrets, where like they only let certain people know certain information. So the data is the most secret sauce thing. So you only have allowing only a small set of researchers to perform and access the data. Details, because it will help the larger research community understand the key factors. Yes. Contribute to a more informed debate about the future of foundation. I agree. Open source 100%. Dude, fuck all the closed source companies. We shared preliminary experiments, integrating multimodal capabilities, still under active development. Following the positive outcomes, we publicly release our Llama 3 models in order to accelerate. There it is again, dude. What is going on with plethora? Dude, like, why? Who was obsessed with this word? Societally relevant. Enable the research community to scrutinize our models. Public release plays a key role in responsible development of such models. 100%, dude. Responsible AI is open source AI. We hope that the Llama 3 encourages the industry to embrace the open, responsible development of AGI. Dude, there it is. They end with the word AGI. And then the rest of this is just a bunch of citations. Look at that. Like 20 pages of citations. There you go, guys. That's it. That's the Llama 3 paper, front to back. The Llama 3 herd of models. How's it going? ByCloud. I'm using Paper Pile. These guys. They don't actually pay me for shit, so, I don't necessarily want to promote them, but I use Paper Pile. There's other ones you can use. There's like a Mendeley is a popular one. This live is a plethora of information and value. I agree, dog. Isn't that curve for their prediction of training and not for LLMs in general? Yeah, this isn't like some kind of general S-curve of like all LLMs, but I think it's a good reminder that all technologies are on S-curves, and therefore you can't just do the same thing and expect better and better results. I think we're kind of getting there, which is really what you expect, right? Like if you think about it, what's the TLDR of this paper? The TLDR of this paper is, hey, we 10x'd the amount of tokens and we 10x'd the amount of training time. So 10 times more tokens, and they're higher quality too. 10 times more training, and it's also higher quality, because there's all the little tricks. But then if you actually just look at the results, I don't know if they have a table here for Llama 2, it's like just a little bit better, So, I don't know, that to me kind of confirms the S-curve. So, scaling laws aren't laws, they're hypotheses, and we got to figure out how to get to the next S-curve. I think it's I've said this like probably 10 times in the stream, but I think it's some combination of the Mambos and the LSTMs, right? Like putting those in there, having a different hybrid architecture. I think it's a lot multimodal. So doing pre-training with images and speech as well, that's going to unlock the next 10x in data is going to come from multimodal data. I think there's a lot of images and videos that it has a lot of information there. And I think that there's something with the power, right? Energy. So some kind of the next level of the GPU, right? The same way that what really unlocked a lot of this current performance trend in deep learning is really the GPU, right? Where, hey, now we have this computer that's almost like 10 times better than the previous generation of computers at this specific task. What if we get a energy solution, some kind of fusion energy or like some kind of power plant type thing, which can be tied directly to the data center and gives us the 10x there. So the same way that GPUs, which were used for gaming, were basically the unlocking factor for deep learning, I think the next S-curve might come from some weird place like that as well. And I think that energy is like maybe like the dark horse in that. But I don't know, guys. I don't really know what the fuck I'm talking about. You know, I'm just some guy on the internet. I'm just some human. The highlighting function you use looks really neat. I'm gonna go download it. Yeah, it's pretty cool. You can kind of see all the things there. I also have it on a mouse. You know, I have one of these gaming mice with the little buttons on it, so like I can very easily switch from different colors. So I can switch different colors really easily. So I use different colors for things. Yellow is kind of generic. Blue is kind of numbers. I use purple for the hardware. So I use red for data sets and benchmarks. So I have my own little like color coding that I use to kind of keep track of things. Thanks for this reading and all your shared knowledge. Thanks for the support, Sarah. All right, guys. That's all I got. That's the paper. Hope you guys got something out of that. Thanks, ByCloud, Sarah, Khalil, RandomBot44, Pratyush770. Who else? Brian, Sagar, Omar, Josh, Aries, Primal, Jakai, Schooly Tom Rivsky, Mark B, and Leandro O. Thanks for hanging out. Hope you guys have a great weekend and see you guys later.